The last few videos have dealt with gas power cycles, cycles in which the working fluid remains in the gaseous state throughout the entire cycle. In this video, we're looking at vapor power cycles. In these cycles, the working fluid varies between gas and liquid states. Steam is a very common fluid for these cycles due to its ubiquity and high thermal properties. So we're going to stick to steam cycles in this class. In steam power plants, steam is heated and used to turn a turbine to produce power. The heat can come from various forms of energy and combustion, but we are really only interested in what is happening to the steam. Like in previous cases, we're just going to treat this combustion as a heat addition process, regardless of whether it comes from nuclear, coal, or whatever. Optimally, we would like to use the Carnot cycle for this process. Remember that the Carnot cycle is the most efficient cycle between two temperature reservoirs. This cycle requires reversible heating and phase transition from liquid to gas in process 1 to 2, isentropic expansion between 2 and 3, reversible phase change back to liquid from 3 to 4, and an isentropic compression to get back from 4 to the initial state. Processes 1 to 2 and 3 to 4 can be approximated as reversible, but this approximation is best at a low maximum temperature, which is bad for the thermal efficiency. Process 2 to 3 can be approximated as isentropic, but the quality of the steam decreases during this process, which is not good for the turbine blades. They want pure vapor, not liquid. And finally, the isentropic compression process is a bit of a problem because just like the turbine, the compressor works best for only one phase. In terms of the TS diagram, what we want is there to be a straight horizontal and vertical lines everywhere, but we also want them to start and end on the saturated vapor line. So we can have 1 to 2 accomplish this, as seen here, or we can have 3 to 4 accomplish this, as seen here, but we can never have both. So bottom line is that we can't make the Carnot cycle work for this process. These issues can be resolved by using superheated steam into the turbine so that it remains gaseous, then by completely condensing the steam into water before moving into the compressor, which is actually a pump in this case. Pumps are compressors for liquids. This thermodynamic cycle is called the Rankine cycle. This is the ideal cycle for vapor power cycles. This consists of 4 internally reversible processes. First, an isentropic compression of liquid water through a pump from 1 to 2. Then, a constant pressure heat addition in a boiler from 2 to 3, which turns the liquid water into superheated steam. Third, we have isentropic expansion of the steam in a turbine from 3 to 4. As usual, this is where the power is generated from this cycle. And finally, the steam goes into a condenser, where it is turned back into liquid water from 4 to 1. This is shown on this TS diagram here. At state 1, water is a saturated liquid. After the pump, at state 2, it is then a compressed liquid. This slightly raises the temperature of the water. Note that this increase is exaggerated here on this TS diagram. The boiler then turns this into a superheated vapor at state 3. The turbine then expands and cools the water isentropically while extracting energy. This leaves the water as a high quality saturated liquid vapor mix at state 4. This is then condensed into liquid form in the condenser back to state 1. This is accomplished by rejecting heat to the surroundings. This just shows a recap of what I just described on the previous TS diagram. Remember also that the area under the diagram represents energy. Specifically, the area under the 2-3 curve is the heat addition from the boiler, while the area under 4-1 is the heat rejected. And because this is a closed system, the difference between the two is the net work produced. Now, performing the energy analysis on the cycle, the work that needs to be put into the pump is given by the change in enthalpy, H2 minus H1, which is also equal to the specific volume times the pressure difference, P2 minus P1. The heat added from the boiler is also the change in enthalpy, so Qn equals H3 minus H2. The work out of the turbine is similarly the change in enthalpy, H3 minus H4. And finally, the heat out of the condenser is H4 minus H1. Note that these are all per unit mass. To do the calculations, the values of the enthalpies are usually found using the steam tables. A4, A5, A6, etc., knowing the phase and pressures and or temperatures at each state. From the first law, we have work and heats coming in and out. There are no changes in kinetic or potential energies. So from the first law, we have Q in minus Q out plus W in minus W out equals HE minus HI, which for this closed system is going to be equal to 0. As usual, the thermal efficiency is given by A to R equals W net over Q in, or 1 minus Q out over Q in, and W net equals W out from the turbine minus W in to the pump, and is equal to Q in minus Q out. The efficiency of electrical power plants in the US is sometimes given as a heat rate. This is how much heat is required in BTUs for the power plant to generate 1 kilowatt hour of electrical energy. The smaller this number, the more efficient the plant is. Using the various unit conversions and ignoring all losses, the efficiency can then be expressed as A to TH equals 3,412 over the heat rate. The ideal power cycle seen previously ignores all sources of loss and irreversibilities. In real life, these factors exist. They come from fluid friction through the piping components, which reduces the pressure of the steam. This requires more work from the pump to account for this loss of pressure. There's also some heat loss of the fluid through these connections, which again means we need to add more heat in from the boiler to make up for this loss. These can be seen in these TS diagrams here, where the lines are no longer nice and horizontal or vertical due to the various losses and irreversibilities. These actual values can then be compared to the idealized isentropic values as shown on this other TS diagram down here, where you have isentropic and actual values for state 4 and state 2. There are a few things that can be done to increase the efficiency of this cycle. The simplest is to have the highest temperature difference, which means increasing the boiler temperature and decreasing the condenser temperature. In practice, this is done by either lowering the condenser pressure, superheating the steam, and or increasing the boiler pressure. However, these can also sometimes include some unwanted effects, such as decreasing the quality of the steam. We can also do things similar to the improved Brayton cycle, such as reheating and regeneration, or some new things like cogeneration or using a combined gas-vapor cycle. We won't actually get to any of these improvements in this class, but more information can be found in Chapter 10. So that is the basics of vapor power systems. Now that we are at the end of this video, here's your pre-lecture example for the day. As usual, please bring any questions you may have to class.